All right, today we're plugging into a topic that is literally all around you, but you probably never see it: the Great Electrical Divide. It's the showdown between the NEC and the IEC. Let's get right into it. So, it all kicks off with a super common travel headache. We've all been there, right? You pack your favorite device, you get to your hotel on the other side of the world, and the plug just won't fit. Or, even worse, you use a cheap adapter and zap, you've just fried your gadget. Well, that little problem, it's just the tip of a massive iceberg, and underneath it are two completely different worlds of electrical thinking. So first up in one corner, we've got the NEC. That's the National Electrical Code. This is the big kahuna in the United States. You can think of it as the ultimate rule book for electricians. Its main job, its whole reason for being, is the safe installation of the entire electrical system. Everything from the big panel in your basement all the way to that outlet in your wall. And in the other corner, we have the global player, the IEC, or the International Electrotechnical Commission. Now, the IEC doesn't really care how your house is wired. Instead, it creates standards for the stuff itself: the motor, the circuit breaker, the appliance you're holding. It's all about making sure that a product built in Germany is going to work safely and perfectly in Japan or South Africa or Brazil. Okay, so just how different are these two? Well, let's break it down by the numbers, because this is where you're going to really start to see the divide. The most basic, fundamental difference is the power itself. In the US, following the NEC, you're getting 120 volts, and that electricity is pulsing at 60 hertz. But in most of the rest of the world, following IEC standards, it's almost double the voltage at 230 volts, and it's pulsing a bit slower at 50 hertz. This right here is the #1 reason your devices might not work when you travel. They're literally built for a different kind of electrical current. And it doesn't stop there. Get this. Even the way they measure the thickness of a wire is completely different. The NEC uses something called American Wire Gauge, or AWG. But the IEC, they use a simple, straightforward metric system: the area of the wire in square millimeters. It's almost like one system is speaking in inches and feet while the other is speaking in meters. They're just not on the same page. These different standards naturally lead to different kinds of equipment. Components you see in the US that are aligned with the NEC, well, they're often big, they're heavy, they're built like absolute tanks for tough industrial jobs. On the other hand, IEC components are usually way more compact, they're modular, and they're designed to react super fast to any problems. It's kind of like American muscle versus European precision engineering, different tools for different philosophies. But, these differences go way deeper than just numbers and sizes. We're actually talking about two fundamentally different philosophies when it comes to keeping you safe. The NEC's entire philosophy is built on a top-down view. It's not just worried about one little switch or one outlet. The goal is to make sure the entire electrical installation, the whole shebang, is basically a fortress of safety. A huge part of this is something called the Equipment Grounding Conductor, or EGC. Just think of it as a dedicated safety lane on an electrical highway. It runs right alongside the power wires, and if anything goes wrong, that stray electricity has an easy escape route to the ground, which trips the breaker and stops you from getting a nasty shock. And when things get really dangerous, say in a factory with flammable gases in the air, the NEC uses a simple two-question system. Question 1, what is the hazard? Is it gas, dust, or something else? They call that the class. And question 2, is that hazard normally floating around or only if something breaks? That's the division. It's a very straightforward way to categorize risk. Now, the IEC, it totally flips that script. Its philosophy is all about a bottom-up approach. The idea is if you make every single individual component incredibly safe, then the system you build with them has to be safe too. So for the IEC, safety starts at the micro level. And their big safety tool is the protective earth, or PE. This system uses a concept called equipotential bonding, which is a really fancy way of saying they connect all the metal parts of all the equipment together. Why? So everything is at the exact same voltage level, and that makes it pretty much impossible for you to get a shock by touching two different metal things at the same time. For those same hazardous areas, the IEC uses a zone system, but instead of asking what the hazard is, it asks how often it's there. Zone 0 is where a hazard is pretty much always present, Zone 1 is where it's around sometimes, and Zone 2 is where it's not likely, but it's still possible. It's a much more granular approach that's all about the probability of danger. Okay, so we've dug into the tech specs and the safety theories, but what does any of this mean out in the real world? For the folks actually building factories, designing our products, and keeping the lights on? Well, the choice really boils down to context. If you're building a huge, heavy-duty factory in North America and you need gear that can really take a beating day in and day out, components that follow the NEC are almost always the way to go. But if you're designing a sleek, compact product that's going to be sold all over the world, then the space-saving, cost-efficient, and globally recognized IEC standard is the no-brainer. And here's a perfect example of why that matters. Just picture a massive oil rig out in the middle of the ocean. You might have complex equipment from 10, 15 different countries all working together. The IEC standard is what makes that possible. It's the common language that allows all those different pieces to talk to each other safely. So, let's just do a quick final breakdown. NEC, it's mainly for North America. It's focused on the installation, uses measurements like AWG, a class/division system for hazards, and an EGC wire for grounding. IEC, it's global, focuses on the equipment itself, uses metric, a zone system for hazards, and protective earth for grounding. See? They're two very different paths, but they're both trying to get to the same destination, a safe and reliable electrical world. And here is maybe the most crucial difference of all. In the United States, the NEC isn't just a friendly suggestion. It's the law. State and local governments adopt it and enforce it. The IEC, on the other hand, is a set of standards. It's adopted voluntarily. Countries choose to use it, or it's required in a contract for an international project. It's the difference between a rulebook and a handshake. So when you boil this whole thing down, the choice between these two giants really comes down to one single question. Is your focus local or is it global? Are you wiring a building according to the specific laws of a specific place? That's NEC territory. Or are you designing a product that needs to work anywhere on Earth? That is a job for the IEC. And that leaves us with a really fascinating question to chew on. In a world that gets more and more interconnected every single day, with global supply chains and international projects just being the norm, do these two separate paths still make sense? Do you think we'll ever see one single universal standard for electricity? Now that is something to think about.